Okay, so is this too loud? I can go a little bit below. Yeah, so I will talk first about terminology. Actually, I'll go all the way through the terminology because of my fear that if I use words without their definition, then we all have different pictures and different meaning of that, and that's not only English. There are other reasons too. So, first of all, to focus on the workshop and its defined scope, I copied here the scope I saw in the invitation, and the red letters are the key words. So, reasonably uncertainty estimates, whatever reasonably is to somebody. Calculations, so we do not want to concentrate on the estimates of uncertainties for experiments. Theoretical is here too, theoretical data. For fusion and astrophysical plasmas, therefore our users are modelers of plasma codes, and we want to talk on the accuracy of AMO data to be used in the plasma modeling codes over many orders of magnitude, from astrophysicists, so we are talking about probably 10 kelvins to 100 millions kelvins when we are talking about core of DT fusion. So once we mention energy scale, we immediately define time scale and spatial scale. So we are talking about many orders of magnitude of time scale, starting from femtosecond, going all the way to years. Spatial, from sub-nano, going all the way to meters. And in order to do this, we do need consistent integration of all processes and scales. So something that we can call integrated AMOscience. And what is that AMOscience? Well, it's we want accurate studies of interactions of electrons, atoms, molecules, photons in many body environment typically, including complex collision physics of plasma surface interactions, because boundary cannot be avoided in the wording of our Madam Speaker. Box cannot be avoided. So I will pay mostly attention to the box. So let's start with the simplest keywords model. That's use of abstraction to approximate a phenomenon, keeping some of its essential features. It may result in analytical representation of the phenomena. In some simple cases, have to be compatible with the rest of the known world, and it has to use the parameters of the observable reality. Now, what is simulation? Well, it's a computational or numerical end approach to the phenomena that is defined by the model. It can combine, unlike efforts to do analytical explanation, several models. We can make more complex models. We can include statistics. We can practically do numerical experiments that have all features of a real experiment, except that it is idealized. and it has internally accurate parameters. Comparison of our simulation, prediction, and experimental measurement is intuitive definition of something that we call uncertainty. So uncertainty would be maximum deviation of the calculated or measured quantity from the true value. The true value is problematic, of course, we usually don't know it, but something that we believe as a true value of an observable. Okay? And by its source, uncertainty could be aleatoric and epistemic. So here we are to a little closer story of the uncertainty. So aleatoric uncertainty is caused by inherent randomness of a phenomenon. It's usually described by some probability distribution, and it can be eliminated whatever we do. It's there. And I understood that from the announcement that we have to mostly deal with our own data, so I apologize that I was using mostly my own data, though I know that concurrently many of your data can be used as examples. Here is one example that is obtained about 10 days ago, which is creation of protective layer of deuterium when you bombard pre-damaged, but that's not essential, monocrystal of deuterium monocrystal of tungsten by deuterium and 25 electron volt. Now 25 electron volt is here because we cannot have too big box. This particular example is about 2 nanometers and 13,000 atoms, 2 nanometers depth, I think. If I increase the energy, that means I increase the spatial scale, because the depth of penetration increases, and you don't want to have artificial reflection from the boundary. Of course, there is XY periodicity and so on, and so it's all standard. So this is nicely seen in DIFFER, which is a plasma surface project in Netherlands recently, and there is a publication about that. This width that you see of that layer is not really as the experiment thinks and sees as a surface layer. Now it's a layer in a depth that corresponds to the penetration for that particular energy, and since each particle there is about I think 8,000 deuterium atoms that are used here in this numerical experiment. So they make a collision cascade. Most of them actually reflect out, find a way out. Some of them get bounds inside the lattice and create this layer that might be a wall for more of the deuterium or heavier particle to come in, and also prevents diffusion from the surface in. That was seen also in carbon about 7-8 years ago. So it always creates an island. You can see in 2D picture also this way. That corresponds to the impact energy. So if it is 30 electron volt, the deformation of the interface as well as the depth is bigger, 5 electron volts less, but that's all. It always creates that. And even if you do quantum classical molecular dynamics, where is here shown for lithium, carbon, oxygen mixture, you again get a similar picture somewhat wider. So this is an example of aleatoric uncertainty that cannot be avoided. And this is usually a case for the fusion surfaces, fusion plasma-facing surfaces, because most of the events in plasma that carry energy give that energy to the wall. There is no way for some volume distribution of the energy. It always ends at the surface. So for that point of view, the surface is equally important as plasma inside, and maybe even more important because it contains boundary conditions, and as you know, boundary conditions are those that define physics. Of course, plasma, that is very complex thing with multitude of temperatures, of species, of angles. In addition, there are neutrons there. So that is all attacking this poor surface that is nothing but a big molecule. It's not a material. It's an entity. It's an interface. It belongs to two worlds, to plasma and material. Okay, and its depth is a couple of nanometers. So for most experimentalists, it's 0. But these 10 nanometers, 5 nanometers, 1 nanometer is really a battlefield of many processes that are here listed. Okay, so a little bit more intuition what is happening is here shown on the movie, where you have a hydrocarbon bombarded by deuterium, and you see the surface is changing. So there is a reflection, there is a molecule formed. Here it's methyl, CH3. Yeah? Next time it will be something else, depending on depth and the chemistry that happens. Important thing here is that even under flux of 10 to 25 particles, like you expect in ITER on the diverter, you have on a typical 10 nanometer square impact surface about 1 particle each 10 nanoseconds. For the majority of particles in the diverter that are usually below 100 electron-volt energy, all processes, including the most complicated chemical sputtering, end in about 50 seconds, 50 picoseconds. Sorry. So then you have a big break. So what we have? You have interaction of one particle, even with this huge flux, with the surface. But the story is not so easy, because the previous one changed the target. So you have dynamical target. The target is changing all the time, okay? And so you do have atomistic processes essentially. So it's AMO physics, nice. Heavy particle interacting with a big molecule, but with dynamical target. And that contains memory of all its previous life. Okay, it's a little bit more moving. This is a quantum mechanical, and this one quantum classical molecular dynamics, where this is mixture of lithium, carbon, and so on. Essentially, the processes that are happening are very similar, and I'm not going to stay more on that. It's just for your picture. To describe what is the complexity of the chemical sputtering, which causes all this randomness, is projectile, which can be all different types in plasma, impinging energy that has all distributions, internal state of projectile, both electronic, vibrational if it is a molecule, rotational, isotopic effects, flux density that is varying, target is changing, it's changing its surface microstructure. The worst case is carbon because it's so reactive. Okay, so you have crystalline and amorphous and polycrystalline that are changeable on the surface. You have a different hydrogenation level, which causes different hybridization, sp, sp2, sp3, and these are crucial to what hydrocarbons you're going to get, temperatures, and so on. Okay, so this is a calculated content of different sp hybrids, sp2, sp, sp3, in case where you start from majority of sp2, which means amorphous structure created from graphite, like ATJ graphite is. Okay, and it turns out that that structure completely reflects, if you follow as a function of energy, impact energy, what is coming out, because the zero order processes, which is when you have end structure of, let's say, sp2, will be the most dominant one in comparison to those that, let's say, cut sp and then has to make another attachment of H. No. We know in quantum physics it's always zero order that is the strong one. And you can see how the surface really morphologically changing, but nevertheless you do reach, because the things are happening deeper than on the real surface, you still reach as a function of fluence, which means in function of time, a steady state, a kind of steady state, which is slowly changing because you are losing particles in the model. Okay, now comes another source of that we mentioned, which is this synergy of all possible constituents of plasma. So, nice, beautiful, most beautiful experiment in this area is the one done by Jakob's group in Germany, in Max Planck. So when they bombarded graphene, it's not graphene, sorry, it's amorphous graphite. When they bombarded it with only hydrogen, they barely saw anything at this energy. When they bombarded it with only argon, well, they saw some physical sputtering at some energy high enough. But when they mixed a little bit of argon in carbon, they got significant sputtering. This is experiment, and it's clear why. The argon did the job of breaking the bonds, which will be then reacting with the hydrogen to make hydrocarbons, and they would use the voids that were created by argon to get out. Okay, so it was a multiple function. Another example is in tungsten, where you have creation of this hydrogen layer or helium layer. Actually, when you mix helium and hydrogen, helium goes faster deeper into the material, and then it prevents hydrogen to go in. And that's something found by experiments. So you with a little bit of helium in the hydrogen beam, you much less bubble the surface of the tungsten. So can it be simulated? Yes. I mean, it's in initial conditions. So rather than bombarding the surface with one angle, one energy, you bombard it with many. Of course, it costs, but you bombard it with some distribution. For example, Maxwell distribution at 10,000 Kelvin, and you get the results, of course, that are different than just adding linearly the effects of different energies, because the effect of plasma is non-linear superposition, it's non-linear synergy, and that's very important. because that says one unfortunate fact that we cannot, from simple experiments or simple calculation, but just adding processes, conclude what is happening in the competition of them. So we have to do the plasma irradiation, and that's why people have created about 10 linear plasma machines that are less complicated than toroidal plasmas, and so it's possible to make some kind of plasma irradiation, plasma experiments. Now, this is at input. That's what we were talking before. So you have some distribution that is Maxwell here, random distribution. And what you get in the output, of course, distribution too. Okay, and here is just the measured, actually calculated. Okay, rotational energy, and here is center mass energy. They both have different temperatures, different distributions. But that's all that we can find by calculation. That's nice. Another kind of uncertainty is epistemic uncertainty. That's what essentially our madam speaker was talking about. So that's due to lack of understanding. We do not know what is happening. We don't know what the processes are. So we are including not enough phenomena to get sensible output. And an example is here on, is this word? Yeah, on tungsten. Okay, so trim, that is a simple binary code, and that is not reading any change into the target, predict that this would be about increase of dPA or cumulative damage in the tungsten by bombardment with self ions, with tungsten again, which are, as you know from basic mechanics, most efficient for transiting energy from impact to the target. Okay, the same masses transfer the energy in head-on collision completely. Okay, very light one, likely to reflect. Okay, so what we see here is that if you do it right with MD, with one order potentials, which means complete angular dependent potentials. I'm not saying ideal, but much better. Then you get saturation. So interstitials and vacancies are saturating. You actually, if you look in time, you see there is a jump of creation of interstitials and vacancies, and then it drops, jump, drops, jump, drops, and that's all happening on the scale that depends on the impact energy. In this case, impact energy is 1 kilowatt, so it's scale 10 picoseconds. And why? I mean, these two movies show why. Okay, so you see that you create first a lot of. Is it not running? Or it's 10? It's not running. Okay, let me run this. It's easy. So this is 10 kilowatts. Okay, you see how many Frankfurt pairs, which means pairs of vacancies, interstitials, are created, and then they start recombining. Trim doesn't see it. So you get in 30 picoseconds, tens, hundreds less number of defects than you have originally, than you would get with trim. Although you can claim trim has 0.1% accuracy, well, but not epistemic. Okay, now this is about experiment, and it's so close to my heart I have to show it. I go fast, okay? So this is a creation of fuzz, nanofuzz, when you're bombarding with a particular above threshold fluence, in particular above threshold flux, and heated tungsten, about 1000 Kelvin, okay, with energies of deuterium that are 25 electron-volts. Okay, so you see, it's like a hair, and that's very dangerous stuff, because you don't know what will happen if it happens in a reactor. I mean, it will definitely change the properties of retention. It might change the properties of reflection, of exchange energy generally, of diffusion and everything. So, general situation is that you don't have normal impact of deuterium in the reactor. All these experiments were done under normal impact. Okay, so Fred Mayer from ORNL last year finally did the experiment I hoped he would do, and this is normal impact, then 43 degrees impact. You see here is growing in the direction of the impact, which erases a number of theories that were made in the time when only normal impacts were there. And then comes next experiment. He created a normal impact here and then bombarded it with angular. And what happens? Haircut. So where this tungsten went, where did it go? It went to plasma. Generally, it will go to plasma. What does it mean? Well, it might mean end of tungsten. Okay, so but I'm not aware. Maybe you are. That anybody has seen in any of tungsten reactors this kind of hair. So that might be that because of the different angles of plasma, it was created and destroyed immediately, or something else. I don't know. Now, this is a very nice example of epistemic uncertainty too, which is it has been known for 10 years, 15 years that lithium wall conditioning. What does it mean? A couple of tenths of nanometers on carbon, okay, and carbon has no idea whether it is lithium or carbon, or hydrogen. It sucks in all lithium. So you cannot really have a layer of lithium on carbon. I mean, it always intercalates inside. Whether it is graphite or it is amorphous carbon, it always happens. It goes in. Okay, so you lithiate carbon, and it was found in a number of tokamak machines that lithiation of carbon has improved energy confinement time, and it also improved recycling and suppressed erosion of the carbon. A big deal, I mean, of the whole story with carbon. So maybe that can contain good solution, and that's the basis actually of the NSTX tokamak that is in Princeton National Lab. So what is here nice is that you are controlling 1 meter plasma with tenths of nanometers of lithium. So nice sentence, okay? But nobody understood why is it happening, except that experiments from Purdue have seen that there is some oxygen chemistry happening, but lithium was the main player, so why oxygen? So, well, the theory is needed here. Lithium is different than others because it has very low electronegativity, 0.94, which means it doesn't like to take any electron from others, it's giver. Oxygen, on the other hand, is taker. I mean, it takes to it has a high electron affinity, in other words. Okay, so unlike lithium, it has no. It has low. So lithium in contact with all fusion materials have that tendency to have low electronegativity, and with tungsten, with carbon, with everything, with oxygen, of course, and hydrogen. So everything becomes negatively charged in presence of lithium that becomes positively charged. So suddenly you have, unlike any other molecular dynamics, long-range forces. Whether they are Lennard-Jones kind or Coulomb kind, but they are long range. They are both there, okay? And it completely changes the dynamics and chemistry. So what does it mean? If this charge plays such a big role, we cannot do classical molecular dynamics. Why? Because in classical molecular dynamics, you label at the beginning each atom with charge. It could be 0, or it could be half, could be 1, could be 1.5, but you label it. Okay, you cannot change it. It's not changing, and it's known that charges are changing with coordinates of the complex coordinate of the whole system. So how can you do that? The only way is to solve the quantum solution of this complex system at each time step. Freeze motion of heavy particles, solve adiabatic problem, and then calculate forces and release it for 0 to femtosecond, freeze it, and then so that's what is done here. Okay. When we have done that, and of course you have to repeat it for thousands of trajectories, because surface is not a simple object, so you do need Monte Carlo. And what we got is that retention increases and reflection decreases exactly as it was found in all these experiments. And besides, when you have only lithium and not oxygen, then erosion actually increases, because the lithium is a less binder than carbon even, okay? So about factor 2. So you do need oxygen. So what we did, we put 20% of oxygen, and then did calculation, and then got these results, okay? So the only problem was nobody believed that there is 20% of oxygen at the surface. If you take a regular carbon, it's 5% of oxygen. If you put lithium, it intercalates deeply in, and you get in average about 8% of oxygen. So where is 20? Well, again came these people from Purdue, did now a careful XPS experiment, and they found that at the surface, a couple of nanometers from the interface, you get a strong accumulation of oxygen, because when you bombard it by deuterium, not before bombardment, after bombardment, because by bombardment you stimulate diffusion from depth, and it goes up, and since now lithium is in, there is a long-term attraction between oxygen that is negative and lithium is positive, and so lithium doesn't allow oxygen to leave. If you remove lithium, then oxygen will leave. That's the way how to clean the carbon of oxygen. Just bombard it and it will go. But if there is lithium, it will not go. It will stay at the surface, and then you get the effects as we have, because our calculation is really applying to 1 to nanometers. Why? Because we cannot afford more for quantum classical molecular dynamics. So the question is, their experiments are 500 electron volts. Our experiment could afford 5 electron volts. What to do now? Okay, do experiment at different energies. We were convinced that chemistry is happening at the end of the cascade, when the deuterium practically thermalizes with the material. I mean, what is that chemistry that is happening at 5 electron volt? None. I mean, it's happening really at very low energies. So if it is so, then it doesn't matter whether you bombard it with 500 or 5 electron volts. It will happen only deeper when it is 500 electron volts. But it will be the same chemistry, and that's exactly what they see from the shape of this curve, not going into detail. Okay. Now, what is another source of epistemic uncertainty? It is in all molecular dynamics calculations potential. Potential is key. Its connection with the reality. So, as good potential is, as much good is your molecular dynamics. Okay. So, the best developed potential is thank you. The best developed potential is the one for hydrocarbons. It has been developing for 20 plus years, okay, and it contains a lot of good features, 400 semi-classical, semi-empirical parameters. It's not perfect, but it's best. Okay, and even with that potential, we were compared, let's say, the reflection coefficient with TRIM and with RIBO and A-RIBO, which are two colors, let's say, of carbon potential, hydrocarbon potential. You see how big differences are even for these two colors at low energies. So, and this is the feeling of the lattice with the deuterium. So A-RIBO has long-range interactions. RIBO has short-range interactions. That's the difference. No charge, but long-range. Okay. So what do we expect from mixed material potential? So it has to reproduce bonding characteristic for solid carbon, for example, in this case, yeah, as well as various composite molecules in the fitting database. Okay, it has to yield binding energies and bond lengths that are reasonably transferable, okay, to systems that are not in the fitting base. Otherwise, there is no point. It has to allow covalent bonds and breaking, therefore chemistry, and it, in addition, doesn't have to be, shouldn't be computational intensive. Okay, so these are the elements, for example, that are used. Some elements, not all, that are used in creation of hydrocarbon potential. That's how we build other potentials too. Okay, so now we come to the concluding almost. So what do we expect from the uncertainty quantification, which is a new branch of math that has been developed in the last 10 years. So DOE is heavily funding it through one of the SciDAC institutes. And so far it has been applied, according to literature, to atmospheric, therefore climate research, so this kind of systems, and static material properties, the design of materials, okay? But not for AMO on dynamics. And that's what we want to do, okay? We want to, given a model, simply here, where X are input, A is set of parameters, and if we assume that there is an interval of X that could be distribution or just unknown, we want to get to predict in advance interval for Y, and that's what UQ is really doing. Okay, and I'm suggesting that that expansion of UQ to AMO data comes into conclusions of this workshop, and we already have two esteemed scientists that started working on that. I would suggest literature that is connected to Dakota project of Sandia Laboratories, because there is a program there, code, that they claim is general enough that can be adapted relatively easily to UQ in this environment. And so now validation is issue for both theory and experiment, and interestingly, that's not a straight road. Okay, so this is our calculation for H2 plus H charge transfer, and this is the experiment about 5 years ago, and now this is the same story this year at IMAP. Okay, so you see that it's not necessarily that theory has to approach the experiment. It could be that experiment has to approach to theory, and so have that in mind. Experiment is not absolute benchmark, and the verification, that's simple. Okay, so that's computer code, and other tools that we are using really doing what we want, and I want to stress this: consistency and unitarity is extremely important. So you want to put on the same footing all processes. In here we have proton H2 plus collision with vibrational dynamics included. It's fully quantum, and you can see here as you change the initial vibrational state, your picture of the wood is changing. Here, of course, elastic processes, viscosity and momentum transfer are dominating when you start from the ground state. But once you go up, okay, so you see that charge transfer is dominated, and even excitation, and then dissociation is dominating charge transfer, and momentum transfer from the high state is nothing. I mean, you can neglect elastic processes. Okay, so. Okay, so what accuracy will need to be learned from fusion modelers. That's the point here, and they are not very active in that. So this is calculation that is done by David Koster, and our Detlev writer, who is here, is also another fusion plasma modeler who is responding to this, and this shows how much the data for temperature and concentration change between database and database, the same database, ADAS database, between 95 and 98 and 2000. Okay, so these are minimal changes in data, but these are data for hydrogen, for most abundant one. Okay, so that's the trick. I mean, yeah, so I'll summarize with this, okay? That's what we don't want. This is a nice paper that Savin did a couple of years ago, and he compared the cross-section for charge transfer in collision of proton on H2 that are used by astrophysics plasma modelers. And what you see here is a range of 11 orders of magnitude. Why that? Because in absence of data that are standardized and recommended, everybody produce data that are best fitting their own theory to prove their point. That's not how atomic physics works. Okay, so somewhere here, like here, are even our data in the mid-gold. So that's exactly why I believe we are here to produce the way to secure, validate data and be able to recommend them for the use of the modelers. Otherwise, we are out of physics, we are in metaphysics. Thank you very much, and sorry about this.